We have already proved complex Jordan form. Now we wrap up the real case in one episode. Because apparently matrices needed one final paperwork packet. The punchline is simple. Over real numbers, eigenvalues may disappear, and 2x2 blocks show up to cover the mess. Over complex numbers, we proved that every operator on a finite-dimensional complex vector space has Jordan form. Over real numbers, only one basic problem appears. A real operator may have no real eigenvalue. That is the entire disturbance. One missing eigenvalue, and suddenly the room needs 2x2 furniture. The standard example is 90-degree rotation in the real plane. Its matrix A is 0, -1, 1, 0. The characteristic polynomial is z squared plus 1. That polynomial has no real root, so this real matrix has no real eigenvalue. It rotates every line away from itself, which is rude but legal. To understand the real case, temporarily complexify the real vector space. If T complexified has eigenvalue lambda with eigenvector z, then the conjugate vector has eigenvalue conjugate lambda. So non-real complex eigenvalues occur in conjugate pairs. Lambda equals A plus bi and its conjugate A minus bi. The real form has to package each pair together. Separating them would require leaving the real world. And apparently we are pretending to be disciplined today. Write a complex eigenvector z as x plus iy, where x and y are real vectors. If lambda equals A plus bi, then comparing real and imaginary parts gives Tx equals Ax minus by, and Ty equals Bx plus Ay. So the real span of x and y is invariant under T. A complex line has become a real plane. Same information, worse packaging. In the basis x, y, the matrix is the 2x2 block complex numbers of A, B. Depending on the basis order or sign convention, you may see the signs of B flipped. Same beast, different haircut. Real Jordan form has two kinds of blocks. Real eigenvalues give the usual Jordan blocks, with lambda on the diagonal and ones above the diagonal. Non-real conjugate pairs give 2x2 real blocks complex numbers of A, B. For a longer complex Jordan chain, the real block is a block matrix with complex numbers on the diagonal and I2 above the diagonal. So a complex Jordan block for A plus bi turns into a real block twice as large. Congratulations! The price of staying real is doubling the luggage. The correct real statement is that every real linear operator has a real basis in which the matrix is block diagonal with these two kinds of blocks. 1x1 real Jordan blocks for real eigenvalues, and 2x2 block chains for non-real conjugate pairs. We are moving quickly here because the real version is important, but usually less pleasant to compute with. If complex scalars are allowed, ordinary Jordan form is cleaner. If the problem must stay real, these 2x2 blocks preserve the same information. So the real form is not a new plot. It is the complex plot translated back into real coordinates, with extra boxes because apparently translation needed storage fees. This closes the Jordan form arc. Next we start inner product spaces, where vector spaces finally get geometry, length, angle, orthogonality, and other luxuries algebra had been pretending not to need. Jordan form told us how operators behave after choosing clever bases. Inner product spaces ask for bases that are not only clever, but geometrically civilized. Over complex numbers, Jordan form uses ordinary Jordan blocks. Over real numbers, Non-real eigenvalues come in conjugate pairs and become 2 by 2 real blocks. That is the real Jordan form story. Next stop, inner product spaces, where linear algebra tries putting on shoes before walking into geometry.